Hi, I'm Tim Paterek, and you're watching the Lugless frame building video. In this video, we're going to build a bicycle frame completely under power. And at all possible times, I will try to use different types of power tools like the milling machine and grinders and whatever I can, so that you can see another option for building a bicycle frame. Okay, first of all, let's take a look at the printout, and right after that we'll take a look at the drawing. First of all, the printout, which is generated by the Paterek computer program, gives you a complete geometrical printout, it gives you a components printout, and it also does receipts for you. It's also a record keeper. This computer program is available from United Bicycle Tool Supply at a very inexpensive price. Basically, they're selling it for pretty much the cost of reproducing the program. You'll use this program, this printout, this geometrical printout, to do your drawing. Here we are at the drawing board, and if you're going to make your drawing by hand, there are some things you're going to want to have. First of all, your paper source. A roll of newsprint. You can buy that at a local newspaper. Just get an end of a roll of newsprint, or some high-quality butcher paper or something like that. Anyway, something that the lines will show up well on. I really wouldn't recommend something like craft paper, because the lines won't show up on that brown color. Also, you're going to need, a nice quality pencil. 2H lead is fine, and something that'll make fairly fine lines for you. You'll need a compass to draw the bottom bracket shell, and you'll need a beam compass to draw in the diameter of the front wheel. These are also available as little units that slide onto a wooden yardstick, so you can just slide them right on and convert a yardstick into a beam compass. Some high quality straight edges. This is a nice metric one side, English on the other side, stainless steel rule. And then I also have, that one is a 60 centimeter, and I have a meter stick right here, and those make excellent straight edges for drawing your different lines. Then you'll want to have a protractor, and I always think the bigger the better. A larger protractor has larger spaces between the increments here, and it's easier to see your actual measurement with a larger protractor. So the bigger the better on the protractor. Those of you that have the luxury of a drafting table, if you have a drafting machine on your drafting table, such as this one's actually it's an antique now, but this one was made by Vemco, and you can draw straight lines just by putting your pencil right up against the horizontal rule, holding your pencil in one place and just moving the whole drafting machine to the side, and you'll have a nice straight horizontal line. So let's just move that out of the way, and we'll discuss the different parts of our drawing. Okay, first things, what I did was I used the printout from the Paterek computer program. And the Paterek computer program, by the way, is available for a free download at my website, www.timpaterek.com. And the program is free. And when you download it, install it on Windows 98 or before. It was originally programmed for DOS, so it's an older program, but it'll do everything that you need to do as a beginning frame builder. It'll generate worksheets, it'll generate geometrical specs, it'll let you redesign the frame over and over until you get what you want. It'll generate customer and merchant receipts, and it's free. Just go to my site and download it. Let's take a look here. First thing, when you get the printout, the geometrical printout from the Paterek program, you'll go in this order. First, you'll draw two horizontal lines. One horizontal line will be the bottom bracket center line, and the next horizontal line will be the bottom bracket drop. So you'll come up from the bottom bracket center line up to the axles, and that distance from this horizontal line down to this horizontal line is your bottom bracket drop, and that's one of the first readouts on your printout. Then you'll figure out your seat tube angle, and of course I use the protractor to figure out my seat tube angle. It's 73 degrees off horizontal. And then run your center line up, draw your two sides of your seat tube, draw those in, and then you'll want to mark the next item on your printout, and that will be your seat tube length. This particular one is 56 centimeters. And then you'll want to draw your horizontal top tube in. Always draw a horizontal top tube. That can be changed later. All you have to do is just lay a straight edge in there, and after the whole frame is drawn, you can move that straight edge to wherever you want that top tube to be. But in designing the frame, make sure the top tube is horizontal. Now, you'll draw a straight line, horizontal, for the center line of the top tube, and then you'll put one line on top of that and one line below that for the edges of your top tube. If it's a 1-inch top tube, one will be a 1/2 inch above and the other will be a 1/2 inch below. If it's an 1 1/8" top tube, be 9/16 and 9/16. Then the next item on your printout will be your top tube length, and that would be from the center of the seat tube to the center of the head tube, and you'll put a mark there. And then the next printout item would be your head tube angle. So you'll want to, if you're working on a table like this, you can adjust your head tube angle like so and read it right off the scale here, and then you can draw your head tube lines in like that. If you're working with a protractor, just do it manually with a protractor, and you're going to draw in your head tube center line right here, right down the center. That'll go through the top tube length. Then you'll put your back of your head tube, the back edge of your head tube here, and the front edge of your head tube here. These can vary. You know, if it's a standard lugged road bike with an 1¼ inch head tube, it'd be 5/8 on each side of the center line. Of course, you're doing lugless, so you're going to have to measure your head tube to find out what the radius is that you want to be away from that center line. Go down your center line here and measure out the amount of your fork rake out to here, and drop a parallel line down to the axle line right here. Then that's where your beam compass comes in. Use your beam compass to go from the center of that axle line and strike an arc up there to find the top of your tire. And that tire is right, there we go. It's right there. So I've got about 1 centimeter of clearance. This is going to be a bike that's going to take short reach road brakes. This particular drawing, the one we'll be building in the video is going to have a lot more clearance because that is a Unicrown. But this particular drawing has 1 centimeter of clearance. It's also set up for a Henry James crown, which is 2 centimeters up here. And then we've got 14 millimeters right here for the bottom stack height. And then back here we've got 1 centimeter for the intercept, the head tube, down tube intercept, where the bottom of the down tube hits the back of the head tube. And I use a little trick to draw this final set of lines in. What I do is I found this works great for 1 1/8" down tubes. This is exactly 1 1/8 inch, and what I did was I put a little notch. Can we take a close look at that little notch right there? I put a little notch right in the center of that, and I lay that notch right in the center of the bottom bracket shell, where the center lines cross. And then I lay the bottom edge up here. I lay the bottom edge right at my intercept, and when I get that in place, I just strike my 2 lines, and it finds exactly where the down tube needs to be. And I've found over the years that different straight edges will give me different diameter down tubes. This one's perfect for an 1 3/8" down tube, this meter stick. I just take the whole of the meter stick, put it in the center of the bottom bracket shell, lay this on my intercept, and strike my 2 lines, and I've got an 1 3/8" down tube. This particular one right here does a perfect 1.25 inch down tube. Again, put my hole right on the center of the bottom bracket shell, lay my rule up against the intercept, and strike right there. Incidentally, a good intercept right up here, your head tube, down tube intercept, a good intercept for lugless, particularly fillet brazed lugless, would be about 13 millimeters. 13 millimeter intercept here. So then you have your drawing. Your drawing's all set to go, and let's go ahead and go to the table. The stone table, there are a variety of different things that you can use as a surface table in building your frame. This is a really nice one. It's about 4 by 6 feet, and it's large enough to build tandems. Of course, a lot of you are probably starting out just building single frames, but there are a variety of different things you can use for surface tables. A large table saw. Just drop the blade out of sight, and you could use a table saw top as your surface table to build your frame. You could probably find some Blanchard ground aluminum. Aluminum is not as stable as stone. The most stable surface will be a stone surface table made out of granite. There are some old printers tables around from the days when they used to set type, and those are made out of marble. Those are lapped, and those are very flat. The next best would be cast iron. Cast iron is very stable, and there are lots of things. You could probably find something in a junkyard, maybe have it re-Blanchard ground, or just clean it up or something. The next best thing would be you can make your own table. You could take some quarter-inch thick cold rolled steel and weld a web work underneath, kind of a skirt around the edges and a web work underneath, and you could take that in, have that Blanchard ground or precision ground, either way, and that would make a very good surface table. Aluminum, they do make some Blanchard ground aluminum. You can buy ground aluminum. You could go into an aluminum supply house and just order a piece of aluminum, say probably about 1 inch thick by 24 by 30, and just make sure you're getting ground aluminum, cast and ground aluminum, and that's very flat. Again, the most stable temperature-wise and warpage and so on and so forth is stone, then cast iron, then steel, then aluminum or stainless steel. Aluminum and stainless steel are the ones that are more susceptible to warpage from temperature changes. First of all, what we need to do is, let's take a look here. I've got 4 different size tubes here to demonstrate a principle to you. We need to suspend our frame above our drawing in a precision manner so that all tubes are lying in the same plane. And if we take our vernier height gauge here and we take a reading, and this just happens to be 51 millimeters on the nose, and then if we take the diameter here, this one is 25.4, so that's a 1 inch tube. 25.4, half of that is 12.7. So I had 51 millimeters above the table minus the radius of the tube, 12.7, equals this tube, the center line of this tube right here down through the center is sitting 38.3 above this table. If I go over to this big one over here, take a measurement here, this one is 64.7. 64.7 to the top. Now, 64.7, it's a 35, so that'd be a 1 3/8. 35 millimeter, so 35 millimeter, half of that is 17.5. So minus 17.5 equals 47.2. This is 47.2 the center line is 47.2 above the table. And here's a good demonstration of the problem we're running into. They should have the same center line. And so what's going to need to be done is we're going to have to put a build-up underneath this one to bring it up so it has the same center line as this one, which is 47.2. There are a lot of things you can use for build-ups. There are some precision shim materials that are made, and you can order them from KBC Tool or MSC or various other places on the web. I like to use my own shims made out of plastic. Plastic has a lot of continuity as far as thickness goes, and so we can use plastic. You can measure your plastic. These particular pieces of plastic give me a 2.25 millimeters thickness, and so if I put 2 of them, I know I've got 4.5. So that's now 4.5 above where it used to be. This makes great shim material. This is a manila envelope, and so you can. These are 0.3 thickness. So 1, 2, 3 of them would almost be a millimeter. And another good thing for shim material is just computer paper. In this case, I have some graph paper that just came off a tablet. And this is usually about 0.1, yeah, right on the nose. 0.1 millimeter thickness right there. So, 3 of these manilas and 1 of that would be exactly a millimeter. Okay, we're getting close. Let's put in another plastic, and then let's take our reading here. And we have 58.8. 58.8, and we want 47.2. So 58.8 minus the radius, 12.7, equals, we got 46.1. We want 47.2. So let's try taking some out and putting some in. Let's take this out and put another plastic in and see what we have here. We have, this is 60.2. Okay, 60.2 minus 12.7 equals, we have 47.5. We can do, we can play around here. We need 47.2. We're a little bit high. We could raise this one up. We know that's 0.3 right there. 47.5, 47.5. These two have, you can see if you slide them in toward each other, they have the same thickness or same height above the table now. And so you'll want to go around your frame and make sure that all of your tubes for your frame are all the same height above the table. So when it's suspended, when you're working above the drawing, your frame will be all in one plane as you're working. Let's go on and start working on the general prep. Before we start on our general prep, let's talk a little bit about the milling machine. The milling machine, this particular one is a Jet. It's one of their smaller models, but the milling machine is a very versatile machine. It's actually the only machine in the world that has the capability to replicate itself. And it can make a variety of different cuts. It can make different grooves and channels and whatever, round bottom channels, square bottom channels, dovetail channels. It's amazing what this machine can do. And for bicycle frame builders, probably the two biggest applications for the milling machine would be, one, using cutters like these. This is made by Strawberry, or what used to be Strawberry, now is Terra Nova Cycles in Portland. These cutters made by Mackenzie Tool Sharpening Service for Strawberry are made of high-speed steel, and they're what I use to miter the tubes, and I do it on the milling machine. They come in different sizes. I'm holding 1.125 in my right hand, and I'm holding an 1.25 in my left hand, and there's an 1.375 in the quill right now. That's one major application of the milling machine. The other major application of the milling machine for the bicycle frame builder is cutting slots. This is a slitting and slotting tool, and it's held in an R8 collet, which will slide right up inside there, and very positive grip when the milling machine holds it. And this particular one is just the right width to cut a slot in a rear chainstay for the dropout tab. And so that's the other application. Here's a thinner slitting and slotting saw. This one can be used, well, I use this particular one to make my tubing blocks. And this one is only 1/16 of an inch wide. So the two major applications for the milling machine in bicycle frame building would be mitering your joints and slotting other joints. So also you'll need jigs, fixtures. I have a chainstay mitering fixture that I've used for many years. It's fairly simple. You'll see it in operation later on in the video. One thing that we can use a lot in the making of fixtures and jigs to fit onto the milling machine are toggle clamps. And these toggle clamps are available in a variety of different designs. You've got the horizontal ones that lay out flat and they stay out of the way in case you have something that has to move over the top. You have others that push from the side, kind of a plunger type setup. You have others that grab on and pull. Quite a few different varieties of toggle clamps, and those are made by the most common brand name for those is the DeStaco company, and you can probably find them online. And there are some cheaper knockoffs that are coming from some of the third world countries, but I like buying the DeStaco clamps myself. You can buy them from KBC Tool, MSC, Palm Abrasive. There are a whole bunch of different places, and they're all listed in the resource section of my book. So with that in mind, let's go ahead and start working on the general prep.
Take a look at some fixtures that can be used on the milling machine. First of all, this one is for slotting the end of a unicrown fork blade. And as you can see, I'm holding a slitting and slotting saw in my hand. This can be mounted with an R8 collet into the quill of the milling machine and then passed across the end of the blade, thus cutting a slot for the front dropout. You can see it's mounted up here and ready to move into place to cut that slot. Most of the fixtures are made with aluminum plate, which is easy to machine. Notice the use of the toggle clamp to hold it in place. Comes out, goes back in quite quickly. There's a piece at the back that holds it in place, keeps it from twisting, so the slot is not out of line with the curve. And the machine can just be dialed right in. There's a little peg back there that the R8 collet drops down and touches to get just the right height to make the cut. This cut would be made at a pretty slow speed, under 100 RPM. Going too fast could burn up the cutter and could also overheat the end of the tube. Here we have another fixture that holds a single bend mountain type chainstay in place. And as you can see, there's the stay with the oval section and the bend. You can see the oval right there. It's a pretty popular chainstay to use on mountain bikes. Notice again the use of toggle clamps to hold it in place. The toggle clamps can hold things in place quickly and easily. Also, that slot back there was cut by dragging a end mill, a hogging mill, at an angle. If you drag a hogging mill at an angle, it will actually cut an oval rather than a part of a circle. And that oval, of course, if you get it just right, will match that oval section of the chainstay. Here we go, we'll clamp it right in. Those clamps should be fairly tight and set so they kind of snap into place. Give it a little bit of a hit. There we go. And the other one, same thing, nice and snug. Again, down at this end, the cutter has to be set at the right height, and there is a little peg right there. And the cutter comes down, the R8 collet comes down, bumps that little peg to get the right height. And then we run the cutter back and forward across the end of that stay. Also, there's up milling and down milling, so you should do your down milling rather than up milling when making these cuts. Here we have a fixture that holds two 14 millimeter seat stays in place, and they poke in the back end, slide through there, and then the toggle clamp holds them in place, held in the vise, and there's the peg that the R8 collet hits and goes through and slots both seat stays at the same time. Here we have a fixture that will allow us to do round oval round chain stays, and the V-shaped parts that I'm pointing to will hold the oval section of the chain stays in place and keep them from twisting. Notice the chain stays go into the round holes, oval section lays in the V's, and then the toggle clamp holds down the ends of the chain stays. It mounts just like the other ones, and there's the peg right there that the R8 collet comes down and bumps against to find the right height. Here's a fixture that's designed for cutting the slot in the bottom of traditional road fork blades. Notice the use of a Trado fork crown. That's a Chinelli Trado fork crown that was cut in half and modified and mounted to the aluminum plate. The fork blades fit right in. The bottom opens up. The fork blades fit right into the Trado fork crown, and then the toggle clamp will hold down the blade for the final cut. You have to make sure it's in there nice and snug. Here's another handy fixture that I made. Notice I'm sliding a top tube into place. This fixture is designed to miter each end of a 73-degree seat tube where both ends are parallel with each other. It's fairly light, easy to move around, and the tube slides in quite easily. The toggle clamps hold it in place, snap it into place, and one end gets cut first. You cut the rough end, cut the rough cut off of there to rough length, and then you flip it around and stick the other end in and cut the other end. This one is specifically made for 1-inch diameter tubing. The way it's made, you would have to use a different fixture for each diameter top tube that you wanted to cut. Notice at one end right there we have a dummy head tube sitting at a 17-degree angle. Let's take it over to the milling machine, and it gets clamped right into the vise of the milling machine. And notice that the head of the milling machine is tilted at 17 degrees, which is 17 degrees off of 90 is 73. And remember, this fixture is made for cutting a 73-degree parallel top tube. We'll clamp it into place and drop our cutter down a little bit, drop it down far enough so that we can hit that little peg on the back side. Go over there and hit that peg with the 1 1/4 inch cutter, and we know we'll be on center. Bring the cutter up, move the tool over the top of the tube, and we're going to cut the head tube end. We don't feed with the knee when we do this. We have to feed with the quill when we're set at an angle. Flip the tube over, slide it back in after the cut is done, and it will bottom out against that dummy head tube back there. And of course clamp it back in place with the toggle clamps. And at this point we would change the cutter to an 1 1/8 cutter to match the seat tube diameter. and we can mark, there's a ruler on the fixture, and if we mark the length on the ruler, this is designed so that the mark will be right at the valley of the cut. And then we move the cutter back right to that mark and bring it down with the quill. Again, you have to feed with the quill and not the knee when you're cutting at an angle. Here we have some tubing blocks. Bicycle Research makes some really nice tubing blocks. I like to take their blocks and drill and tap them, and so that I can screw the two blocks together. That way they stay on the tube that I'm placing them on. I always use them in sets of two. So right here I have two 1-inch diameter blocks, and I have 2 1 1/8 blocks here. I've made tubing blocks in several different sizes, all the way up to 1 3/4 inch for tandem boom tubes. The Bicycle Research, I don't believe I can make those go any bigger than 1 3/8. I have bored out a few to 1 3/8. Notice how they're connected together with the screws. Tubing blocks can also be made out of wood if you want. I prefer aluminum. It's easy to work with. The tubing block can be held in the vise. You can cramp it down as tight as you want, and you won't distort the round cross-section of the tube, because the tubing block is protecting the tube. We want to have about 3 inches sticking out from the face of the block for locating the center of the cutter above the center of the tube. Right now we've got a 40 millimeter diameter cutter in the quill, and I'm taking a piece of paper here, and I'm using the paper as a feeler gauge, and I'm going to run that tube closer and closer to that cutter until that piece of paper feels just almost like it's going to tear. And of course, because machines like this have a backlash factor, you want to do this on the forward stroke. You don't want to back that cutter off, because it'll make your dial read incorrectly by as much as 20 thousandths of an inch. So get it on the forward stroke, just so it's almost ready to tear, and that'll mean that the cutter is about 3 thousandths of an inch away from the edge of the tube. As long as you can slide that in there really tight, because paper is has good continuity for thickness. And as a general rule, a piece of 20-pound bond paper is about 3 thousandths of an inch thick. Now we're going to have to figure out how much to move that cutter over to be over the center of the tube. And so we're going to set our dial here. I set the dial for 3 thousandths of an inch under 0, which allows for the thickness of the paper. Now with the knee, I'll drop down the table of the milling machine so the cutter will clear. And I've got a little chart that I've made, and what it does is it tells me how much I move the cutter when the tube is a certain diameter and the cutter is a certain diameter. Basically what it means is you move radius plus the 3 thousandths for the paper. And so we'll figure that out. The dial is calibrated in 200 thousandths of an inch, and so I'm counting 2, 4, 6, 8, 10, 12. And then I come to the end. Notice I don't back it off. I keep going in a forward direction to avoid that problem of backlash. You may have noticed that I also locked the cross feed with the lever underneath on the left. And now the longitudinal feed, we can lock that too. Notice I'm doing a right angle cut. This is for the bottom bracket shell. The head of the milling machine is not set at an angle, so I'm going to feed with the knee. I like to use chlorinated cutting fluid. It has chlorine and sulfur in it. Probably not the best smoke to breathe when it starts heating up, but it does give a very much better quality cut, and it does keep the cutters nice and cool as you're using them. You can also get various different types of spray attachments that will apply the oil in a mist for you. You just aim them at the area, and you don't have to use an extra hand to hold them as you're making your cut. It's never bothered me to use a squirt bottle, so old dog, new tricks. I just continue to use the old squirt bottle method. It's also important, I do not like using anything that contains a lard base in my cutting fluid. That will stink up your whole shop. It'll fill the shop with smoke. I would not recommend using lard-based cutting oil for anything other than hand-fed speeds. Now we're going to turn our milling machine on. We have to be set at the lowest possible speed, under 100 RPM preferably. If you can't get down slow enough, it is possible to feather the switch on the milling machine to keep your speed running slowly. Now I feed right there so that the oil is kind of pulled right into the area where the cut is being made, and at the same time I'm feeding up with the knee. The knee of the milling machine, fed from below, is a much more positive and accurate feed than the quill. The quill is up on the right, and it makes the milling machine act as though it were a drill press. Whenever I can, I always try to feed with the knee rather than the quill. We're getting a little smoke coming off of there, but basically a high-speed steel cutter like this cuts beautifully on chrome moly steel. You can't use high-speed steel on heat-treated tubing. If you're using heat-treated tubing, you'll have to go out and get some carbide cutters. And here we are. We take it out, and there's our chip. We break the chip off, and there's our finished miter. Let's check out this miter with our bottom bracket shell, which incidentally is the same size as the cutter, 40 millimeters. Nice clean fit, no light gaps through there or anything. Now we're going to clean the burrs off the end of this tube. They're quite sharp and you could cut your finger on them kind of badly. So what I like to do is I like to kind of shoe shine it with some emery cloth strips. I like to buy 50-yard rolls of emery cloth strips. This is a brand name called VSM. My favorite brand is 3M. It works great. It holds up for long periods of time. 1-inch wide rolls, and I usually keep quite an assortment of it around. 80 grit, 60 grit, 100 grit. For polishing, I go all the way down to 500 grit. That's for polishing stainless or getting something ready to take in for chroming. Anyway, here we have about an 18-inch strip, and I usually don't tear them off any shorter than that. Anything shorter than that kind of gets wasted around the shop. Shoe shining works great for a round surface. Notice that the tubing block is still in place. I have not removed it. And I'm just shoe shining. Not only am I removing that burr around the edge, which can really cut you quite badly, but I'm also shining up that area, which is prepping it for the brass brazing that'll take place later. Shoe shining works well on circular objects. For anything that's irregular in shape, I wouldn't recommend shoe shining. Right now we're kind of cleaning that oil residue out of the inside there. There's no need to have cutting oil burning in the shop while we're brazing. Another thing that you need to do is you need to take the peaks down just a little bit on the miters. The peaks sticking up right there in those two spots. The peaks can literally vaporize on you during brazing, or if you're TIG welding, those peaks can disappear on you. So if you just take them down just a little bit, make that metal there just a little bit thicker where it meets the bottom bracket shell, you'll get a more solid joint. And there it is. It's all ready to braze the bottom bracket shell on. Here's a protractor. I actually got it at a pawn shop, and I kind of modified it. I silver brazed that little piece right on there permanently. The blade is no longer removable, and it's very handy for locating angles off the drawing and transferring those angles to the milling machine. And right now I'm going to find the angle at the lower head lug joint where the down tube and the head tube meet. I'm taking the acute angle there. That's the obtuse angle up there. I want the acute angle down there. It's just the way I set them up on my milling machine. I always cut the acute angle on the milling machine. And after I get my angle, I tighten it up, tighten the screw there in the center so that the unit will not go out of adjustment while I'm working. And basically I've just lifted that angle right off my drawing. And that angle will be transferred to the milling machine to cut that lower head lug joint. Here we are. We're going to bump that protractor against the tube and against the cutter like so. We'll have to move it to get at the right angle. We'll kind of approach a little bit closer. And I've just got the tube snugged up in the vise right now. So I can, tap it with my finger and get it just right so I don't see any light between the cutter and the blade of the protractor. And once I get that tight enough, then I can torque down that vise nice and tight. And there we are. We're somewhere around 60 degrees. Usually that lower head lug is set between 57 and 62 degrees on most bikes. Now, before I was showing you how to make this cut with the head of the milling machine sitting at an angle, and we fed with the quill. Here's an R8 collet, and how the cutter will fit into an R8 collet. The R8 collet is tapered, and it fits up into a tapered hole. And then up on top, there's a drawbar, and you tighten that up there. Hold the brake on the milling machine, and take your wrench and torque down the drawbar. It doesn't take a lot to torque that tight because an R8 collet holds a piece very efficiently. It doesn't have to be really torqued a lot. Probably not much more than you would torque a set of axle nuts on a coaster brake bicycle. All right, now we're going to relocate our center. So we're going to go back, bring the cutter back, bring the tube up, and we're going to bump the tube into the side of the cutter. And then we're going to take that paper. That paper, again, is 3/1000 of an inch thick. And we're going to use the paper as a feeler gauge. There we go. Slide it in there. And we want them just tight enough so the paper's almost ready to rip. And you can kind of tell by feel. Just about there it is. So we know that the edge of the cutter is 3/1000 of an inch away from the edge of the tube, and I've just set my dial at 3/1000 under 0. I'm going to drop the table down so I can move the tube under the cutter. Again, I'm going to check my chart, diameter of the tube and the diameter of the cutter. Radius plus radius is going to give us our cutter movement, plus 3/1000 for the thickness of the paper. And we're going to move over again. This is this is calibrated 200,000 per turn, 200,000 per turn. I kind of count in my head 2, 4, 6, 8, 10, and so on. And right there, that's where we're supposed to be. Lock the cross feed. And then we're going to we're also going to lock the longitudinal feed, but not until we get our length on that tube. There's that cross feed underneath there. Kind of hard to see, but it definitely has to be locked before making the cut, or the cutter can walk over your tube, just almost like a gear, like a rack and pinion gear. It'll go right over the top of that tube and move the tube as it's doing it. So the locks are very important, both longitudinal and cross feed. All right, we're going to make our cut. Here we can feed with the knee or the quill. When I'm doing a vertical cut like this one, the tube is tilted, but the cutter is moving vertically. When I'm doing a vertical cut, I prefer to use the knee down lower left underneath the table. Much more positive feed, and that went through there quite nicely. Use plenty of oil. Don't skimp on your oil. I like to buy my oil in gallon bottles. You save your money quite well. We're gonna run just a little bit more on this one. Probably didn't see it because of the splice, but I did advance the longitudinal feed just a little bit more because I didn't take quite enough on the last cut. And there we have our miter. This time that that particular cutter is the same diameter as the head tube. We loosen up the vise, and there we are. We've got a piece we have to break off, a chip we have to break off that the cutter usually leaves there. Here again, we have to deburr the piece. Those are really sharp there. You wouldn't want to run that into your hand. And again, shoe shining works really well. For this particular sanding procedure, I usually use between an 80 and 100 grit emery cloth strip. Always use 1 inch wide. If you want to use them narrow, they're very easy to rip lengthwise. And there we go. That's going to be a lot safer to handle now. And again, right there, those peaks. We don't want those peaks to be too thin. So we are going to take a file and we're going to remove just a little bit of material on those peaks just to make them a little bit thicker. And we don't want that very sharp area up top to disappear, literally be vaporized during the brazing process. We want to remove that with a file before those things get hot. Those little tips like that will get red really fast, and we don't want things getting red enough to vaporize while we're working. And the same thing goes with TIG. You should take those little tips off of there before you TIG weld also. We will be doing brass brazing on this frame, brass fillet brazing. Take a needle file. We're going to take off just a little bit of a burr there. Always good to have a good selection of files. I've got probably 20 different files that I use at my bench. And there we go. There's our miter. Because we've done it on a machine, it's just at the perfect angle, but we don't have a very good match between the tube, between the head tube and the down tube. And that's taken care of fairly easily. Because the cutters are so expensive and because there are several different brands of head tubes and different diameters of head tubes, we're going to take a set of non-parallel vise jaws. One of them has that little nub on the underside that I just pointed out seconds ago, so that when you put them in the vise, one sits parallel with the vise and the other one doesn't. And so you can crimp a tube like this without putting dimples in it. So we're just going to tweak it just a little bit. Didn't take much. We're going to test it. I think we need a little more. So we're going to put it back in the vise again and give it another little tweak. And we'll pull it out and we'll test it again. And you can get an incredibly good fit here, just 2 or 3 times, and you should have you should be able to adjust that radius just enough so it'll match that head tube, even though the cutter was not the same diameter as the head tube. And you can go in either direction. You can take a cutter that's bigger than the head tube and tweak it one way, or a cutter that's smaller than the head tube and tweak it the other way, and you can adjust that radius so it fits quite nicely. Look at that. You can barely see light gaps through there. Now we're going to determine where we need to put our intercept mark and our vent holes for the head tube. And so we're going to go to the drawing, and we're going to find the bottom of the head tube on the drawing, and then we're going to locate the vent hole. Vent holes are pretty arbitrary. Plus or minus ½ an inch sometimes for your vent hole location. We're painting the edge of that tube with some blue layout dye. Blue layout dye is handy to use because it allows you to make marks. After it dries, you can make marks on the tube, and they show up much better than they would if the tube was completely silver. You can get this blue layout dye, or they do also sell a reddish or a pink layout dye. I guess it's just personal preference. I just buy the blue. And it'll take a minute or so for that stuff to dry. And there's the intercept right there. This one's going to be 13 millimeters. 13 millimeters is a good intercept, head tube, down tube intercept for a lugless fillet braze joint. Of course, if you're building lugged, you know what that intercept is going to be by measuring the lug. And then we find the location for the head tube vent hole, venting out of the down tube. And then we find the location for the top tube vent hole. And you can do this either by just marking manually like so, or if you want to be a little more exact, you can take a vernier height gauge or digital height gauge, whatever kind of height gauge you have, and set that height gauge for those different measurements and just strike it. There is our intercept point right there. And then we can set it for the vent hole that vents into the down tube and strike that one. And then we'll set it for the vent hole that vents into the top tube and we'll strike that one. There we go. We have all three of them marked. Very easy to do with a vernier height gauge. Actually, it's not that much harder to do it with a ruler. And since the tolerances are wide open, go ahead, feel free to use a ruler. Now we're going to mark the locations for the vent holes in the bottom bracket shell. Notice that this bottom bracket shell has a counter bore in one side. Some of them have a counter bore, some of them have a counter sink. Some of them have a little groove machined into the end. This indicates where the left-hand thread is. And on this particular drawing, since the bike is going to our left, on this particular drawing, the left-hand threaded portion will go down. So make sure you look for the left-hand threaded portion and make sure that the bottom bracket shell goes with the left-hand thread down on this particular drawing. Now we're going to paint this area with blue layout dye again. Also, don't do your painting over the area where you're going to be transferring marks, because if you get blue layout dye in your drawing, you're going to have an awful hard time transferring or even finding those areas for marks, because you're going to have blue layout dye all over your drawing. And these V-blocks make beautiful squares. Just tilt a V-block up on end, and we're going to put it against the bottom bracket shell. And first we're locating our chainstay vent holes right there. And then we're going to locate our seat tube vent hole right there. And then we're going to locate our down tube vent hole. I'm using a carbide scribe here. You can get those fairly cheap at Sears Craftsman. Carbide scribes, they have replaceable tips. I think General makes a really nice carbide scribe that you can get at your local auto supply. And there we go. There are our vertical marks. Now, of course, we need to put horizontal marks. This bottom bracket shell is a 68 millimeter shell, so we're going to set our vernier height gauge at 34, which is half of the width of this shell. And of course, a good vernier height gauge or digital height gauge is going to have a nice sharp either carbide or a high-speed steel scribe end on there. That's a sharp end on there that's making that mark for us. And then I usually like to set the chainstay holes at about 15 millimeters in from the edge of the bottom bracket shell. Flip it over and then do the other one. There we go. We have all of our holes marked for the bottom bracket shell. Now we're going to drill these holes. I like to use a center drill. This is a number 5 center drill. It first drills a little tiny pilot hole, and then if you sink the drill a little further, it'll go up to a 7/16. And I like to use nice big vent holes, particularly for the down tube and the top tube and the seat tube. It allows good flow-through ventilation during brazing, and then also allows the metal prep solution to get in and out of the tubes quite easily. So a 7/16 vent hole is a really nice size to use. And so here we are in the milling machine. We can do these holes with a hand drill. We can do them on a drill press. I just like to do things on a milling machine whenever I can. The seat tube and down tube holes and top tube holes will be this number 5 center drill, which is at 7/16 size. Just plunge it all the way down through. Again, you don't have to locate centers here because your tolerance for the location of these holes is really wide open. The bottom bracket shell, again, here we go. There, it's done. That's the head tube. The bottom bracket shell, again, seat tube and down tube holes will be done with the number 5 center drill at 7/16. And we're just going to eyeball them up on those scribe marks. Use cutting oil. Just a dab of cutting oil will do the trick. Always saves wear and tear on your tools to put a couple dabs of cutting oil on there. And then we're going to get the other vent hole for the other main tube. Notice how we've got that little pilot hole forming first, and then that center drill can go right through. It continues cutting right on through and continues to function as a drill even when you hit the larger diameter. Now I like to switch to a number 3 center drill for the chainstay holes because the chainstays are narrower. We wouldn't want to use a 7/16 drill bit for that. And you can either do that by only going part way down with the number 5, or you can plunge cut all the way through with the number 3, which is a 1/4 inch center drill. Well, we're going to just go part way through with the number 5. If you can use the same bit in the milling machine, see, notice I didn't go to the larger diameter. I just stopped at that little tip. If you can continue to use the same bit, it's less setup time, saves you money in the long run. And there we have our chainstay vent holes. You can clamp a bottom bracket shell like this and a lugless head tube fairly tightly in the milling machine vise without having to worry. Here we've got some soft jaws. These particular soft jaws are made out of aluminum plate, about 1/16 inch. You want to make sure to have soft jaws because the steel teeth on your vise jaws will badly scar anything you're working with on that frame. And you can torque down fairly snug on a lugless head tube. Be a little more careful with the lugged head tube though. Now we're going to change that mark for the intercept into a file nick, because that mark from the scribe will get erased or disappear quite easily. So we're going to change that right now to a file nick. And I used a jeweler's file. So even after you sand all of your dirt away and your tube treatment and your layout die, that mark will still be there. And I don't know if you could see it there. I saw it for a second. Our bottom bracket shell, again, we've got a tube treatment on the outside of these tubes, and sometimes, especially if that tube treatment is black, it will prevent our brass from sticking to the surface of the steel. So, and that happens a lot with chromoly aircraft tubing. The surface of the tubes are black. You've got to sand that black stuff off. And it's a good idea to sand anything off of these, get them nice and cleaned up, shoe shine sand these pieces. Get all the contaminants off of there that you can. And there we've got a head tube and a bottom bracket shell. They're all ready to braze. Here's our fork blade. On this particular fork blade, we're using plug-in dropouts. And so we won't have to be cutting any material off the end of the fork blades. We won't have to cut any slots or anything. We've just got those plug-in dropouts, which are really easy to use. This particular set was made for these particular blades. These are a really beefy blade, and they take a really beefy sized dropout. Here's another example. This is a regular tab type dropout in which we would cut a slot, and you have to get that slot just right. You have to make sure that the slot is perpendicular to the curvature at the top of the tube. If you're at all off, you'll have some nasty looking fork swoop when you get done. Next thing we need to do is we need to rake the blades. Here you can see how I've modified my fork bending mandrel. And I've also modified this this crowbar. I put little hooks on the ends, and there's a clamping assembly right there that holds a tip, and that's also a piece of Delrin plastic that's pushing against the actual blade. That's not a piece of aluminum. That's Delrin plastic. I'm eyeballing up so that the curvature at the top of the blade will be perpendicular with our bend. Little cheater bar to get the right twist there. 90 degrees. There you go, 90 degrees right there. Also, notice I've got a piece of scrap, and this is a fairly thick piece of scrap. I'm going to stick in underneath that crowbar, because that crowbar will leave a nasty dimple right there. And it'll literally ruin that blade. So I slide that little scrap under there. That's some thick scrap. That's some 058 wall. There's also a groove that I've cut in the back side of that crowbar so it stays located on that fork blade or on that scrap. Bring it down until it hits the peg. There's a stop peg there, right underneath, right by my knuckle, by my left knuckle. There's a stop peg. And there we have our fork rake. And we're going to go over to the table, and we're going to check that fork rake with the drawing. Put the dropout right on that center point where the front hub is going to be. And we're going to lay the fork blade down so the top of the blade is lining up right between the two lines for the head tube. And the bottom of the blade is laying over the top of the dropout. And we're going to see if those things line up okay. It looks like it might have to go a little more. So we're going to go back over to the fork bending mandrel. Put it back in, clamp it down. As I said earlier, that's a piece of Delrin plastic underneath a little cap of steel. You don't want to be clamping on that tube with steel. I'm going to set that little stop about 1 or 1.5 turns lower. And we're going to go one more time. It's going to automatically stay in the same plane as it bent last time. It's once you put that much bend in a fork blade, it's going to stay in that plane. No matter what you do, you can't modify what plane you're bending in after that. And again, we're going to check it here. Looks good. Sometimes it takes 2 or 3 times to get it right. But it looks like we've got a winner right now. Let's figure out how long our steering column has to be. Dummy headset comes in really handy for this. What we do is we put the dummy headset on the steering column. This particular one is going to be a threaded steering column. Some of the newer forks are using threadless. And I put the dummy headset on there so it matches my drawing. And the bottom end of the steering column is going to be about 4.5 centimeters. You need about 4.5 centimeters for a set of unicrown blades. And then I marked at the top where the top of the headset's going to be. You can use the dummy headset to locate where these points are, and slide your steering column into the dummy headset, lay everything over the top of the drawing, get them to line up with the lines on the drawing. Bottom of the steering column, line that up on the drawing. And when everything lines up just right, you can tell exactly where you're going to make your cut. If you're using a steel dummy headset, the dummy headset can actually be your guide for making your cut. If you want to, you can make your cut with a hacksaw. You can make it on a bandsaw. Here we're doing it with a hacksaw. One thing you have to be really careful of when cutting things in the vise is watch out for those knuckles. Those knuckles can hit the edge of your vise, and boy, you have a real mess on your hand. So that last few strokes, take them slow, take them easy, slow down so you don't hit those knuckles against the side of the vise. There we are. Now, here again, you can cut the, you can square up the end of the cut with a file and using a machinist square to check it, or you could just stick that in the lathe and quickly face off the end of that, and you'll have a nice straight cut on the end, nice and square. Here we're just going to use the machinist square and the file, and we're going to do it just quickly by hand here. We're pretty close, and it's not going to take much work to get that closer. Another excellent way to square off the end of a steering column is to mount the steering column in the vise of the milling machine and just put some kind of an end mill. In this case, we're using a hogging mill, and we're going to put that hogging mill up inside the collet, clamp it down nice and tight, and we're just going to brush the end of that steering column with that hogging mill. And because the quill is square with the table, when we brush the end of that, our tube will be square on the end. As I mentioned earlier, another way to square off the end is to stick it in a lathe and just face the end. All three ways are acceptable ways to square off the end of a tube. Again, do this at low speed. Use plenty of cutting oil so you avoid overheating. You don't want to be throwing blue chips. If you're throwing blue chips, you're either running too fast, or you're taking too big of a cut, or you're not using enough cutting oil. And there we are, nice and square. Square as you can believe. Okay, one other thing that we're going to have to do on this steering column is we need vent holes that'll vent into the tops of the fork blades. And here again, we're going to be using the number 5 center drill. And we're going to place that. We're going to drill these about 2 centimeters up from the bottom of the steering column. And we're going to run that number 5 center drill right through both sides of the steering column. Give it a little bit of cutting oil. We're going to go through the first side. Another little dab of cutting oil. Use the cutting oil and you'll have less snags and chips on that hole when you finish. And we're going to keep on going right through the other side. And this will give us vent holes in both sides of the steering column. Here again, this can be done by hand with a hand drill, or it can be done on the drill press. And shoe shine the ends here. You're going to have some snags on one side from running that drill bit through the other side of that steering column. Get this all prepped for brazing. Take that dark tube treatment off of there. Piece of 100 grit emery cloth strip works fine. Wipe any oil off. The less oil you have on there, the less smoke you'll have in the shop during brazing. Now we might have some sharp edges around the top there, and to lessen the chance of cutting yourself, we can take a deburring tool. Handy little tool, only costs a few dollars. You can get it at machine shop supplies. Next, we're going to slot the chainstay where the dropout fits in, and we want to check it to see if it fits properly into the small end of the chainstay. If it doesn't fit in there, you may have to round the tab just a little bit so it fits in. Now we need to make sure that the dropout slot is perpendicular to the curvature of the chainstay. If not, we'll have some pretty ugly things going on down around there, and there won't be much of a way to correct them after you've cut the slots crooked. So I like to kind of sight in and make sure that that dropout is sitting at the right angle. I'm cutting the slots here. I'm going to cut 2 parallel slots about 8 millimeters deep. And I'm doing this by hand. I know I did show you earlier a slotting tool that I use. However, a slotting tool is good for doing about 15-20 sets at a time. Here we're only doing one. Break the little tabs out from between. And there's your slot. The dropout doesn't fit in there yet. We need to widen it a bit. My favorite brand of files are Nicholson files, and you can get those at a variety of different places, including Home Depot. This is an 8-inch flat Nicholson file, and right now I'm filing to the side more than toward the bottom. I'm trying to cut wide and not cut deep. I tend to make these openings sort of V-shaped. I don't like to make them dovetail shaped. If there's a bit of a dovetail to this, your dropout is going to wobble around in there a lot. But if you make the slot just slightly V-shaped, your dropout will go in and snug right up. We don't want to force fit. We want that dropout to just slip right into place. And as I said, if the slot is just a little bit V-shaped, the dropout snugs up when it hits the bottom of the slot. And we can take a look and see, which way works better, forward or backward. One might look more pleasing than the other. Also keep in mind that we do have a chainstay here that is either a left or a right. So we've got to set it up one way, not the other. That looks pretty good. Lines up nicely. And we're going to take that and set it aside carefully. And then we'll do the other one. Handy set of files I've used in the past are what I call safe files. I take a couple of old files. These are 6-inch flat files. And I run the faces of one file against the belt sander. And I take off all the teeth on the faces. And that one will cut down, but it won't cut wide. This one, I cut the edges off on the belt sander, and that one will cut wide, but it won't cut deep. And so by switching back and forth between these two safe files, it makes it a lot easier to control how much and where you're cutting. After some experience, it's very easy to use a standard file, but the safe files make things a lot easier. After you get both chainstays slotted and the dropouts fitting properly, it's a good idea to line them up with each other and sight across and see that both dropouts are sitting at the same angle. You don't want that axle slot to be cocked one direction on one side of the bike and cocked the other direction on the other side of the bike. So we're going to put them in there. They're all fitted and everything. And let's just sight across and make sure that they line up properly. These are looking pretty good. The left one tends to want to wobble more. The right one is a little bit better balanced and will sit in place better. Now we're going to mark them right side and left side. And the way I do that is at the large end of the chainstay, I put a notch on the right-hand side, and I put a notch on the right-hand dropout so that we know which dropout goes with which stay. And once you get it with the right stay, since there's a bend in the blade, you can't reverse it. It has to go in one direction. Now what I want to do is I want to put a scallop in the end of that blade. This is more for decoration than anything. So I'm going to take, this is a 10-inch round file. 10-inch Nicholson round file, and I'm going to just run that file straight sideways, perpendicular to the center line of that chainstay, and I'm going to cut a scallop right in the end. Put some finishing touches there. We've got a nice looking scallop, 4 little points sticking up on each side of the dropout slot. You want to make sure that those points don't disappear on you, because then things start getting distorted. Let's deburr it with the emery cloth strips, and then let's go down inside with a needle file, and we'll take out any burrs down inside with a round file there. As many of you bicycle mechanics know, we need a little bit of extra clearance on the inside face of the right-hand dropout. That's sprocket clearance inside there. If we don't have that, the chain is going to chew things up inside there. So what we're going to do is we're going to cut off just a little bit, about 5 or 6 millimeters of one side of that scallop. See, it's not a very big piece, just 5 or 6 millimeters. Now let's take and file a little bit of a flat where we just cut that off to get the clearance we need on the belt sander. And now we want to remove any paper-thin burrs inside there, because of those paper-thin burrs heat up while we're silver brazing these dropouts in. Those paper-thin burrs will ruin our flux, and the silver won't stick to them. So we'll break that burr out of there, and then we'll take a jeweler's file and clean the burr off so it's nice and clean all the way around. That'll ensure a very good joint. Clean up inside with a round file, and there we go. There's our clearance. That's what we need for that sprocket. Now we're going to miter the top tube. You notice I'm holding this tight down against the table, and I'm tightening my blocks on here. I'm trying to make sure that the grooves on both sides are roughly the same opening. That way things will be nice and parallel. And make sure that when you tighten those blocks that they don't rock on the table. And if both blocks are sitting flat on the table, you know that when the tube is held each end in the vise, it'll be held in the same plane. We're going to mark for rough cuts here. Going to cut about 2 or 3 centimeters off of each end. If we cut too much off of one end, we could lose the whole butted area of the tube. But if we take part of it off of each end, we lose less of our butted area. And of course, a metal cutting bandsaw can simplify things and make that rough cut quite a bit quicker. There we go, we're all rough cut both ends. Taking the angle off of the drawing, and we're setting up to miter the front end of the top tube. And this is pretty much a repeat of before, using the piece of paper as a feeler gauge and getting things centered up. Everything is all dialed in. We make our cut. This again will be a little bit of a mismatch between the head tube and the cutter, so we're going to tweak this one later too to get this tube to meet the cutter properly. Another problem we're running into with this particular design is that the diameter of the seat tube and the diameter of the top tube are also different. The top tube is actually a larger diameter than the seat tube. So we're actually going to do the opposite of what we did before. We're going to squeeze this in the unparalleled jaws again. We're going to squeeze it down smaller so that we can match the diameter of the seat tube. So we'll check it there. We want to go down to 1.125 so that it matches the diameter of the seat tube. In this case, we're going to do the tweaking before we do the mitering, because we'll run a 1 1/8 cutter through this. We don't want to modify it after, because we do have the right size cutter. and we'll put it back on the table. I've got the jaws, I've got the tubing blocks back on there, and this time that back tubing block, the one that's closer to you, is about 6 inches from the end of the tube, and that's because we don't want to be clamping in the ovalized area of the tube. There's my obtuse angle, there's my acute angle. And as I mentioned before, I always cut from the acute angle side. So I'm going to put that little piece of paper under there so I don't smear blue layout dye all over my drawing. I'd rather get it on a little piece of paper, if anything. And I'm going to mark my miter back there. I'm using the V blocks as squares, and I'm going to use them to locate the tube on the bike. Right now I'm finding the valley of the miter right there, and I'm lining it up with that point at the acute angle at the front. Notice the acute angle at the front is on the top side, the acute angle at the back is on the bottom side. And I use the edge of the V block to find that actual valley of the miter and the top edge of the top tube. Get that all lined up there. Use another V block back here to locate where that valley of the miter is going to be back there. However, I need to locate the tube first, because don't forget we're ovalized where my right hand is. So I need to locate back 6 or 7 inches to get this tube lined up above the drawing. Get it lined up just right. Take your time doing this. You know, the more exact you get it, the less chance there'll be of a messed up cut, or even having to recut a brand new tube. After the tube is on the drawing, we're going to move this V block over to where that acute angle is, which is where the valley of the cut will be. And then we're going to put a little scribe mark right there at the valley of the cut. And there it is. Just quick scribe marks. Doesn't take much because we're using blue layout dye, and it shows up quite well when we're using layout dye. Now we're taking the angle off of the top tube, seat tube angle. Again, we're using the bevel protractor to do that. And we're going to transfer that to the milling machine. Tighten it up, and we'll go over to the milling machine. I'm taking this angle back way behind the tubing block. I didn't take the angle out at the end of the tube because don't forget that tube is distorted, and those edges are no longer parallel with each other. I'm taking a reading, how wide is my tube, because I have to use the actual thickness of where I've squeezed. And this time I'm using a calculator, not my chart, because that tube is not necessarily to the nearest eighth of an inch or the nearest 25.4 millimeters or whatever you're hoping to get. It could be squeezed a little bit more, could be squeezed a little bit less. So we use a calculator at this point to find our center points. And this is pretty much the same as before. Finding that center. And here we are, we're all lined up on center. We're going to turn the machine on, and we're going to start oiling and run that cutter down through. Now we're splitting that mark, that little tiny scribe mark that we made back at that acute angle at the valley of the miter back at the seat tube. And there we go. If we've done everything right, this top tube will be just the right length to fit into that frame. And of course we're going to have to deburr that, and we're going to have to take down the points on those miters a little bit. And also it's not perfectly round, but boy does it fit well. Fits just right. Not perfectly round, so we won't be able to shoe shine it the way we normally do. Our general prep is finished now, so let's review what we've done. We've fitted the front dropouts into the fork blades, and we have drilled the vent holes into the head tube for the top and down tube to vent, and we've marked our intercept. We've drilled 2 holes for the seat and down tubes and 2 holes for the chainstays into the bottom bracket shell. We've mitered the lower head lug joint of the down tube, and we've squished it so it'll meet the head tube properly. We have mitered the bottom of the seat tube to fit with the bottom bracket shell. And we've mitered both ends of the top tube. One end, of course, we squished in one direction so that it fits properly with the seat tube, and the other end we squished in the opposite direction so it fits properly with the head tube. We've slotted and scalloped our chainstays. Both of them, and we've made sure that they fit properly. And we have cut our steering column to length and drilled the vent holes through that will vent into the fork blades.